What I want to discuss in this video is the initial value theorem and the final value theorem. So initial value theorem and final value theorem are important, particularly final value theorem is important in control theory because you're often interested in knowing what happens to your system as time approaches infinity. What is the final value of the state of the system approach? Initial value theorem is perhaps less useful in circuits because it will not take into consideration necessarily the difference between 0 minus and 0 plus and embedded initial conditions. So slightly less useful, but it certainly will give you the initial condition of the system right as switches move and t is equal to 0 plus based on the Laplace transform of whatever you're evaluating in the system, a current, a voltage, whatever. So here's the definition of the initial value theorem given here in this equation. Basically it says that if you have a system that is defined by a Laplace function f of s, if you take the limit of s f of s as s goes to infinity, you get the initial condition on f of t. And that initial condition, you'll notice, is given at 0 plus, not 0 minus. So as an example, assume that we have some function given here by s over s squared plus 4s plus 2. In order to evaluate the initial value, we take the limit as s goes to infinity of s f of s, which then generates the s squared in the numerator. Now, if you're taking the limit of something with a term that goes to infinity, it's infinitely easier to evaluate if the s's are always in the denominator of a fraction as opposed to raised to a power, because it's not clear here. Looks like we're getting infinity over infinity, and that gets a little unclear. So in order to eliminate those powers greater than 0, we multiply by the highest power 1 over it. So we take 1 over s squared, multiplying both numerator and denominator by that, so that all of our s's then appear in the denominator of a fraction. And because s goes to infinity, those terms will then go to 0. So we end up with 1 over 1, or an initial value of 1. And remember, that is at 0 plus, just after the system has switched or turned on. For the final value theorem, it's the same thing, except instead of finding f of 0, we're finding f at infinity. Instead of taking the limit as s goes to infinity, we're taking the limit of s goes to 0. Remember, s is a complex frequency. It has an inverse relationship with t. So if we want t to be infinity, we need to let s go to 0. So we basically repeat the same thing. We have the same fraction, and so we get 0 over 0. The final value then goes to 0. Almost always, if you have a typical function, the final value will approach 0 as far as the transients go. If you have sources in the system or some other forcing function that maintains a value at infinity, then you won't have that approach 0. So if we look here as an example of a function whose final value will not go to 0, we can take this expression, and notice we have this s here in the denominator, so we have a pole at s equals 0. So given the pole at s equals 0, when we evaluate the final value theorem, taking s f of s, when we then multiply by s, these two will cancel, giving us 1 over s plus 2, letting s go to 0, we get 1/2. So to get a final value that is a constant, you've always got to have this s term in the denominator. It's also possible to have a situation where your function goes to infinity as a final value, and that would be an unstable system. So you'll have 3 different options. It's either going to go to 0, it's going to go to a constant, it's going to go to infinity, or in some cases you get something that is undefined because it ends up being like a sinusoid. All right, so that's the initial and final value theorem. That's not hugely important in circuits 2. It is more of a linear systems and feedback and controls topic, but wanted to introduce that to you because feedback and controls can be such an overwhelming class that it's kind of nice to see it before you have so much else to worry about in that particular class. So that's initial value theorem and final value theorem, and they can be found on any